why that is great and everything, people will always talk about Shor algorithm and Grover's algorithm. So Shor algorithm, as we know, that has a lot of applications in factorization. So it can do factorization in polynomial time. On the other hand, Grover's algorithm is kind of a database search. That's the way the paper was written. But it actually goes beyond just saying that it's a database search. What I have planned for today is I'll show you some details, and instead of, so these are all very mathematical topics, obviously. Um, Instead of going too detailed into every mathematical steps, what I'll try to do is to give you more of an intuition of how this algorithm works. I'll definitely share the PDF and everything that I'll show today. You can check the mathematics. We will give you the essence. I'll give you the essence of what that mathematics is about, but I'll not dive too deep into every step of the mathematics, because I mean, somehow it feels to me that things start gets boring if I just keep showing mathematics on every step. And after that, what I have also planned is to show you how to implement Grover's algorithm using Qiskit, and what are the challenges there. There is a lot of challenge involved. So let's go into that. Hopefully, we won't need 2 hours, but let's see. So as we discussed, that the problem that it was initially posed as is a database search problem. So if it is an unstructured database, then so there is no structure to the database. For example, if we know that the database is sorted and I want to search for entry there, I can do this binary search, which is very efficient. But if the database is unsorted, then there is, I mean, it's unstructured, not unsorted. There is no structure that you can actually exploit to find or calculate or easily find some particular element that you are trying to find there. So if that is the case, then what is the best thing that you can do? A deterministic approach will be that I start looking at every position one after another, right? I look into the first position, then if I find it, great. If I don't find it, I look into the second position, and so on. Worst case scenario, I will find it at the end, the last position. I'll find it there. So if there are n elements in the data set, in the worst case, I'll need order of n. Can I do any better using classically? Well, you can, but you cannot change the order. So this calculation shows that, okay, see, if you look into the data set, since it's not structured, since it is, sorry, there is a question. Wait, how do I read the question? Yes, I see. So this is actually one chapter that I was invited to write. So yeah, this actually contains a bit more. I'll share the Grover's part with you, so don't worry about that. Um, so this case here, you can ask that, okay, is it like every time you will find it at the last? Definitely not. I mean, since it is unstructured, I can, even the first element can be the element that I am looking for, the second element can be that. But if you look on average, then also if you do a simple calculation, it will turn out to be this n minus 1 by 2. That is the average number of calls that you need to make to find the element. Now, having said that, does it need to be really a database search? No, right? Think of a problem, some combinatorial optimization problem, some graph theoretic problem, NP problems in NP or something like that. It is it is something like this, right? You have exponentially many solutions. Wait, is it not? Am I not audible?
Audible
Okay,
clearly.
okay. So so think of this. Usually, you will see that whenever we look into database, they kind of write that this capital N is 2 to the power small n. Why so? Because say I am looking into a optimization problem, some problem. NP hard, normal NP, some problem, there are exponentially many solutions, and there is no reason for general cases. We don't know whether one solution is preferable over the other, so there is no real structure to that. Say I am trying to solve a graph theoretic problem which is NP hard. So what is the worst case scenario that I can do? I'll start doing so it's a set kind of problem. You can always write it down like a set kind of problem, and you assign say 0 or 1. There is you assign 0 or 1, and then you try to satisfy some constraint, right? um, if you don't know anything, if there is no nice algorithm that you are aware of, what can you do? You start by assigning everything as 0, and you see whether it's a good solution or it's a valid solution. Then you say, okay, all 0 last is 1, and you keep on changing, and in the worst case you will have to go from all 0 to all 1. So it is kind of like saying that each of this solution is an element in my database that has no structure which I can exploit. And all I can do is I can try out all of them. Why is trying out easier than finding it? Because think of this definition of NP hard or NP complete problems, where we say that if I give you a solution, then it is easy in polynomial time you can verify whether this is a valid solution or not. But finding a solution is difficult. It takes exponential time. But if I give you a solution, you can validate whether it's correct or not in polynomial time. So that's why that's the approach that we will take here. So even though Grover's is kind of celebrated as a database search algorithm, you will see this has been used so widely to solve graph problems and everything, because it's not really a database search. It's this is the way all these interesting problems are casted as a database search problem. So we understand that if I take a classical approach, it will take order of n times, which is order of 2 to the power small n, where capital N is some 2 to the power small n. Can I do any better in a quantum approach? So in quantum approach, I know you have already covered a lot of algorithms, so you know what is an oracle. Um, we will take an oracle approach here. Just for the sake of completeness, you can think of oracle like a like someone who knows everything but has a very annoying character that he or she doesn't want to give you the answer. So only you can ask a question and the oracle will return the answer for that. But he won't. So for example, the oracle has a function if inbuilt, but the oracle will not come and tell you what is that function. If they tell you what is that function, you are done. You will have to keep putting in inputs, you will get outputs, and from there you will have to learn that function, right? This is what we kind of do. And if you think of it, machine learning is exactly this. We learn a hypothesis. If I already knew the hypothesis, I could have done the classification or whatever very easily. Just because I don't know, I have to do this training, which is kind of giving an input and getting an output and kind of trying to learn what that hypothesis H looks like. So here is this oracle that is there, which knows whether it's the solution that you are giving to it, whether it's a valid solution to the problem, or in the database search idea, whether this is the element that you are looking for. And why this is easy, once more to reiterate, because you can think that the oracle is basically trying out your answer, and in polynomial time, it can tell you whether the answer is correct or not. So that's kind of the oracle approach, and we will define the complexity of the problem by the number of times you have to query this oracle. And obviously, we want to do as little as possible. So if I cast the classical approach as a query, you have to do order of n queries to the oracle, where capital N is again 2 to the power small n. So now what changes in quantum? See, what changes in quantum is that qubits are not like basic bits. Qubits can do something more. So there is a concept of having phase of a qubit, right? We know that it can be alpha 0 plus beta 1, it can be alpha 0 minus beta 1, it can be some alpha 0 plus e to the power I theta beta 1, something like this. So this concept that it is not only 0 and 1, there is some associated phase that you can take advantage of. This is something which is different for qubits, which is not present in bits, right? So obviously we will try to take advantage of these things. So we define an oracle like this. Let us suppose that I have, so this is a 2 to the power n, all possible solutions, and this x is my solution. So it's some bits, n bit strings from 0 to 1n, and we prepare our input. So this is the input we will give to the oracle, and oracle will give me some output. So this is the input that we will prepare. So say, for example, if it's a 3 qubit, then maybe 011 is a possible input. I will create a qubit, which is ket 011. I'll give it to the oracle. What the oracle will do is something very interesting. And this is something you can easily understand immediately that this is not doable in a classical scenario. So let's suppose that W is the state that you are looking for. In terms of database search, W is what you are searching. In terms of, say, a combinatorial optimization problem, W is the solution that you are thinking of, or the correct solution, something like that. In general, this W is called a marked state. Marked state. So it is the state which is marked, and you are trying to find out that marked state. So we will call it as marked state henceforth. What this oracle will do, if it will look into x, if the x is the marked state, it will add a phase of -1 to it. Otherwise, it will not do anything. This is what the oracle will do. And you can immediately understand that this is something that a classical computation cannot do. Okay, nice. So what happens if I do this? Why is this so important? So there are basically two steps. One is this phase inversion. The other will be a rotation or a reflection. You will see these are kind of similar, not exactly, kind of similar, and we will see how that comes. So first we will prepare our system in the equal superposition of all the states. So that's very simple. I'll apply Hadamard on all my qubits. Here, 0 basically means n qubits. Although I write it as 0, it is basically 0 tensor n. So if I apply a Hadamard gate, it becomes an equal superposition of all states. Now, this is just a mathematical representation, nothing more. In this equal superposition, there is one marked state and there is everything else. Let's call them bad states. This is perhaps the good state which I am looking for. Everything else is the bad state that I don't care about. So you can actually partition this portion as the good portion, which will have a probability of 1 over root n, and the bad portion. Okay. So does preparing this superposition do anything? Well, no, actually, because if you measure at this point, what is the probability that you will get the good state? That is 1 over n, which since n is 2 to the power small n, it is exponentially low, that the probability that you will get the correct solution. So this step doesn't really do anything very significant, because if you just do a superposition and then measure, the probability that you will get the correct solution is exponentially low. That means you need to repeat this exponentially many times to get a correct solution. Nothing changes from what classical is doing. But now we will look into something like this. So this is the good state. Everything else here is bad state. Pick one element from this bad state, say x1 or something. What is the probability that if you measure this state, you will get the state x1? That is also 1 over 2 to the power small n, right? Every state is equally probable. So this is what we are representing here. So say these are the probabilities. So this bar, this blue bars, they give us the probability that I'll get the state 1, probability that I'll get the state 2 if I measure this one. And since it's an equal superposition, the probability that I'll get any of this state is equal, right? So that's why the height of the bars are the same for all of them. So there are 16, that means it's basically 2 to the power 4. I'm just, the example is 4 here. Small n is equal to 4. So this is what we said here, and this is what the picture is representing pictorially, that the probability that you will get any of this outcome if you measure is the same. Now let's take the average of all these probabilities. It will also be the same, this red dotted line, because everything is the same. So the average is also this. So this will be the average. Fine. So this is what what we understood mathematically here is the same thing that this picture is representing. Now I give this state to the oracle. Remember what the oracle does? The oracle does nothing to the bad states, but it takes the good state and it adds a minus, a phase to that. So I give it to the oracle. What happens? This W portion acquires a phase of -1. Nothing changes here. What happens to this picture? How can I represent this picture now? Any thoughts? How will my figure look like when my state has become this? What is now the probability that I will, if I do this, what is, yes, exactly, flipped. What is now the probability that if I do this, what is the probability that I'll get the good state? It is still 1 over n, right? Just having a minus doesn't change the probability. It's the square of this. So it is still 1 over n, but there is a minus phase. So if I want to represent this, it get flipped like this. So this is how it looks like now. The length of these are still the same. Whatever the length is here, the length is same here, the same length of everything, but this minus basically changes it. The direction changes. Again, once more, you can understand that this has no classical correspondence. If you ask what is happening, like this doesn't seem right. Of course, it doesn't seem like, because this is something that doesn't happen in classical thing. This is purely quantum. You can apply something like this. What happens to the average now? The average will slightly lower, right? Because out of this n states, capital N states, all of them have the same thing. If this state was not there, think of it, if this state were not there, all the states have the same value. So the average would have been this. There is one state that got flipped. This will pull down the average slightly, not too much. Because when I'm thinking of a very large n, there are so many of them which still have the same value, only one of them have flipped. So it will pull down the average slightly. So previously the average was the same here. Now the average goes down slightly. Now what I will do is, this is something called a reflection operator. And the reflection operator in general is defined like this, but let's not go again too much deeper into the mathematics and all. But pictorially speaking, what is happening, the essence of this is very simple. You take this point, you take this straight line. What I mean is, you take this straight line, you are this bar is this much over the straight line, you will just make it this much under the straight line. So however, whatever is the value that is above the straight line, that much value will come to the less of the straight line. So I'll make this bar go down like this. So it's kind of a reflection along this straight line. The height changes, the height lowers basically. What happens to this? It is in a negative direction. The distance from this case is this much. Now when you rotate it across this line, this will shoot up and this will become much higher than the others, right? This is what will happen. Everything else lowered slightly. This one, so the point was, however far you are from this straight line, that much you will go in the opposite direction. So here, as I am seeing that this is this much above the straight line, this will go this much below the straight line. This is this much below the straight line, it will go this much above the straight line. This is what happens. Now if I measure, this state, what is the case? The probability that you will find this state, which I am thinking as the good state here, because this is what we did, right? We changed the phase of W, which is the state that I am looking for. So now if I measure, the probability that I get the good state is higher than the others. This is something that we can understand here. So if I measure it now, the probability that I get the state is higher than this. Previously, it was the same. Now, just after doing this, applying a phase to the good state and reflecting it across the average line. So this average line is actually in reality in a quantum computer, it is denoted like this. It is a 2 psi minus I, where basically psi is the state. So great. Now you see that it suddenly becomes that I have a higher probability of getting the mark state. But but you see, these are not very low. So what can I do? I'll repeat this step again. So now my average is, say, somewhere here. I'll flip along it, it will go down, it will again go down. I'll reduce the depth again and it will again shoot up, something like that, right? So this, if I repeat a few times, then what will happen is these probabilities will get very, very low. This probability will get very high. In general, we can show that these probabilities almost get towards zero, and you can make this to 99% or more. So now you have a very, very high probability that if you measure this state, you will get the correct outcome. You will actually get the correct solution. That's the essence of Grover algorithm, if you think. We will look into another aspect of this, that is through geometric rotation, which is perhaps, to me, it's a bit more intuitive. But this, what we discussed here, is the essence of Grover's algorithm. There is a lot of complicated mathematics that is involved here, fine. But yeah, if you understand the essence of Grover's algorithm, this is it. And you can see, I mean, this is a beautiful. No. So the question is that if the oracle is able to get the mark state in the first hit itself, then shouldn't it be order of one? No. Because what is happening? See, the oracle is not telling you the answer. The oracle knows the answer. The oracle will not tell you. This is how the oracle is defined, right? It knows the answer. So that's, like I said, that it's a very irritating kind of friend. I know everything. I'll not tell you. You know that I know everything, but I'll not tell you. You ask, whatever you ask, I'll reply you that much only. I won't tell you the entire story. So it's a very irritating behavior for someone, but this is how the oracle works like. Oracle knows, but the oracle basically flips. It does nothing else. What you can see outside, you get into a scenario like this. So you have to measure the state. The oracle is not giving you the state. The oracle is just flipping the state. Then you are reflecting it across this average line. Once you have done that, finally you have to measure. And when you measure, yes, the probability here is higher, but these are not close to zero. So that's why in one go, we cannot solve it. We need to repeat this state many, many times so that the other states, which are kind of the bad state, their probability becomes almost close to zero and this becomes close to one. That's kind of the idea. And this is actually a very good example. I feel this is a very, very good example of what it's like. I mean, how a quantum algorithm is different from a classical algorithm. That's why I like this pictorial representation very much, because the steps we discussed, this has no classical equivalence. A classical algorithm cannot work like this. So let's look into the other picture. Let's look into the geometric picture. This, I feel, is slightly more intuitive if we look into the geometric picture. So again, it's the same thing. The oracle looks into the input. If it is the mark state, it will add a -1 phase. Otherwise, it does nothing. I define another u. Again, these are mathematics. We won't go too deep into this. I define another u which will just keep the state unchanged if it is 0 or add a minus if any other state. But this is my main oracle. This is my main oracle, which is like the same thing. I mean, we are just looking in the same problem in just in another angle or something. Now think of this. This is kind of the state that we talked about, the initial superposition state. Yeah, I'll come to how it is order of root n. Yeah, we haven't actually we haven't discussed how many times we need to repeat this operation. We need to repeat this a few times. We will see why this is order of root n. Now again we have this situation where the psi is the equal superposition. I am just writing it that this is the good state, the marked state, these are the bad states, everything. Now if I look into this entire bad state and write it as say psi other. So psi other is the combination of many states which are all my unwanted states. And this is my wanted state. Can you realize that these two are orthogonal? Can you convince yourself that these two are orthogonal? I think you should. So let's look into one. Let's think of an example. Let's say that I have a 2 qubit scenario or 2-bit scenario. So 00011011. Um, let's say 11 is the state that I am looking for. So if I look into 000110, these are all computational basis states. So everyone is orthogonal to each other. Right. So obviously, this state is orthogonal to every state in psi other. So naturally, it is orthogonal to the subspace created by psi other. It is not a single state. It's a subspace created by many others. So if I look into this, it's a exponential dimension space. The way I'll represent this figuratively is this is one psi other. It is one vector which contains many computational states, which is all of them are bad state, and here is a orthogonal line to that, which is the good state, the marked state that we are looking for, W. Now what we will do here, this we can always do, right? This is something we also wrote before in the previous method of going here. I can always write this as cos theta and this as sin theta. And here sine square theta becomes 1 over n. So I can always do that. So I can represent this psi as cos theta psi other and sin theta W. Okay, great. Now we will define two other states. Remember this another u that we defined? It keeps 0 unchanged. For every other state, it adds a minus phase. So this is the u state. U acting on psi. X, sorry. U acting on x. And I am saying that my psi here, psi, how did I get psi? Remember, I applied Hadamard on all the qubits. Let's come here. How did I get the state psi? I applied Hadamard on all the qubits. So psi is basically Hadamard acting on 0. This 0 is basically an n qubit state. So let's come here. What is the inner product of x with h psi? Or think of this, what is the inner product of hx acting on psi? H is its own inverse, so h inverse is h. What is psi? It is h0, so these two h gets cancelled out, so it is x 0, and if x is not equal to 0, then this is 0. If x is equal to 0, then this inner product is 1. Now let's look into this thing, HUH acting on psi. Yeah, that's why, I mean, I understand that becoming a lot of mathematics, but still, just stay with me. What is psi? Psi is H0. Okay, so let's replace psi by H0. Now I have HUH acting before. 2H, they cancel each other out. So HU0. What does U do to 0? We defined that if U doesn't do anything to 0. So U acting on 0 is just 0. So H acting on 0 is again psi. So nothing changes. When you apply this HUH on the state psi, psi is the equal superposition state. nothing happens. The state is still psi. Let's look into the orthogonal state of psi. Okay, let's look into the orthogonal state of psi. What happens? This is H acting on X where X is not 0. So previously we dealt where this is 0, and if I'm saying that this is orthogonal to this, then it should be something other than 0. It can be anything. It can be anything, but it's something other than 0, definitely. So this psi perpendicular is H acting on X. Again, the two H gets cancelled out. Now H U X. What does U do to X if X is not 0? It makes it minus X. So we end up getting minus H of X, and let's call H of X as minus psi orthogonal, because we know that X is orthogonal to 0. If X is not 0, since these are computational basis states, it needs to be orthogonal to 0. So since these two are orthogonal to each other, yes, it's a phase change. Since these two are orthogonal to each other, so I am getting I can write another uh, orthogonal basis here. Say this is psi orthogonal, and let's assume that the the angle between them is theta. We can say that the angle between them, you can actually, I mean, you don't need to really assume, you can show that if you write it like this, and if you take the inner product of psi and psi other, uh, this was psi other, remember, this was psi. So yeah, if you just take the inner product, that becomes theta. Now I apply the oracle. It's again the same thing. What does oracle do? Oracle applies a minus phase to the mark state. What is my state at this point? The initial superposition state, cos theta, psi other, sin theta, w. So when I apply the oracle, what will happen? It will become cos theta psi other minus sin theta w. So if you now look into this, what happens to the state? It becomes like this, right? When I apply the oracle, so previously it was cos theta psi other plus sin theta w. So it was, yes, it's a combination of good and bad state. So it was basically a combination of this and this. Now when I applied the oracle, my w becomes minus w. So now it is a combination of this and minus w. So it is exactly this kind of state that I get after applying the oracle to psi. If this angle is theta, this angle is also theta. Now what happens when you apply this reflection operator? When we talked of reflection here, what happens when you do this reflection operator is that you reflect along this. So what will happen is something like this. When you apply this reflection operator on top of this, it will move like this. It will move 3 theta. So this is theta, this is theta. It will move by another theta along this line. So overall, starting from here, it moves 3 theta. If you think that this was the original state, so we can, what is the point here? If I look into any state psi, since it's an equal superposition, these are the combination of all bad states. This is the combination of the good state. Initially, when you randomly select something, right, the probability that it will go here is very high. So the state is actually very close to this psi other, because we know that if I look into the equal superposition state, if I look into the equal superposition state, the probability that we will get the good state is 1 over 2 to the power n. On the other hand, the probability that we will get one of the bad states is almost one, except for this portion. So if I give it a representation, how should be the representation? This theta is actually very small, exponentially small, because this guy, if you, I mean, the picture is like this to actually make it very legible. Otherwise, if you want to be mathematically accurate, this psi should be very close to psi other. The probability, if I measure at this point, the probability that I'll get one psi other is very high, and the probability that I'll get W is very, very low. But what happens when you do this reflection operator on top of this state? It actually goes 2 theta here. It goes 3 theta along this line. It goes 2 theta here. So what does it mean? What will happen if I measure this state now? So previously, remember, this psi was very close to psi other. Now after I do this rotation, it goes something like this. I mean, again, I have drawn this theta pretty large just to make it legible, but ideally it moves slightly away from psi other. So now if you measure, the probability that you will get W is higher than before. So you can see the same thing happening here. Once you do the phase change by applying the oracle, then you do the reflection, the probability that you get this state has improved somewhat. Before it was the same. The same thing happens here. It has a rotation, and I'll tell you why this rotation thing is good in some time. I'll tell you. Um, this one, so previously it was very close to psi other. Now it moves slightly away from psi other because it has moved away. Um, so the probability that you will get W if you measure it now becomes slightly higher than before. Let's repeat this. This is what we said here. Repeat this till these gets very small. This almost becomes 1. Same thing. Repeat this. Sorry. Repeat this still till this state becomes almost the same as W or exactly same to W. If this becomes exactly same to W or very close to W, then if you measure, the probability that you will get W is 1 or very close to 1. How many times do you need to rotate? That is exactly how many times you will need to repeat this operation, right? And here, when you write it like this, cos theta, sin theta, and everything, you can show that when you do this once, when you do this operation once, it goes something like this, cos 3 theta psi plus sin 3 theta psi. So from only theta, it goes to 3 theta. This is, I mean, looking from here, from psi other, the rotation is 2 theta. But if you look from this U oracle psi, the rotation is 3 theta. So now what we say is there are some basic calculations. Now you can say that you can do some induction kind of calculation to say that if you repeat this k many steps, the state will become cos of 2k plus 1 theta. Yeah, exactly. So the number of rotation makes higher probability for the good state. Yes. So if you repeat this k times, then cos of 2k plus 1 theta it becomes, and sine of 2k plus 1 theta. What do we want? What do we want? We want sine of this. We want this portion to be equal to pi by 2, to be equal to 1 kind of thing. So we want this as pi by 2. And since we started by saying that, this state is actually very close to psi other, so we can do some mathematical approximations. We can say that sine theta is basically equal to theta. So we need 2k plus 1 theta to be equal to pi by 2. And then you can actually see what was theta. Remember, from here we said that if you write it like this, sine theta is basically 1 over root n. So when sine theta is equal to theta, theta is basically 1 over root n. So now you replace theta by 1 over root n, and then you can show that this is essentially pi by 4 times root n. Or in the other sense, how many times do you need to repeat? Order of root n times. In general, it is pi by 4 times root n. So that's how we get that we need to do root n times the rotation, or if you liked the previous angle, the previous thing before, we need to repeat this inversion reflection root n times, so that the probability that I get the marked state becomes almost 1. So that's kind of two ways of visualizing Grover's algorithm. Now, you can ask that why did you suddenly go from that this kind of picture down to this geometrical rotation kind of picture? Because it gives us slightly more information. Let's ask you one question. What is your hunch? So we have understood from here that we need to do this. I'll show you one code. How is the Oracle implemented physically? Um, we will, yeah, thanks for. So we have understood that we need to repeat this order of root n times, and if you do the exact calculation, it's roughly pi by 4 times root n. What if I run it more times? What will happen? What will happen if I do the do this exercise more than pi by 4 times root n? What do you think? Any hunch? Any thoughts? Order does not change. True. Yes. Yes. So it will actually go far away from the mark state. So what will happen? Think. So what am I doing? I am doing this rotation again and again and making it close to W. Once it is already very close to W, if I repeat this step once again, it will actually cross W and go somewhere here. If I repeat it again, it will go somewhere here, here. So what will happen here? It actually started away from W. I did this kind of repetition. I took it very close to W. If I don't stop there, it will actually go away from W. So now your probability of getting the state actually starts reducing. What if I don't stop there? You can actually perhaps understand it right now. I went very close to W. I don't stop there. I am starting to go away from W. I still don't stop. I keep going, keep going. I'll again start coming back to W. So it will become a periodic function. If you don't stop at pi by 4, so initially your probability was very low, say you're starting from down there, very low. You reached 1, probability 1. You don't stop there. You move away from the state. Again, your probability of getting the correct outcome reduces. And then again, it starts coming back. It again becomes 1. This becomes a periodic sinusoidal type of function. So that's why I really like this kind of geometric approach, because it gives you a very direct intuition to what happens if you don't stop. Um, so this is, as you can understand, this is obviously not the only solution if it's a periodic solution, but obviously we want to reduce the number of calls to the oracle. So we will take the minimum number of calls. So just one or two last comments here. If you follow this kind of approach, you will see that the probability of getting the correct answer reaches around 99%, never really 100%. That is actually good enough for all cases. But those people who are from more theory, they actually did some studies and showed that if you are really interested, when you go up to 98 or 99%, and you can actually do another round, but there you want to adjust the reflection rotation properly. Now you cannot do the same kind of rotation. You need some other state. If you rotate around that state, that last 2% remaining, that will also be covered, and you will have a 100% probability of getting the actual mark state. That's one point. Perhaps not very interesting, but definitely it's a nice theoretical and mathematical example. The second point is, what if? So remember, as I started by saying, that we should not think of it really like a database search problem. It is more of something that I am trying to solve an NP hard problem, which would require me exponential time. But using Grover, I can give a quadratic speed up to this. And this is a provable speed up. Like, we are not just running some examples and telling you that, see, it is faster. No, it's a provable, mathematically bounded speed up. So what happens if my problem has more than one solutions? That can happen. So W is not the only state. Sorry. So Here, W is not the only mark state. Maybe there are two mark states, W1 and W2. Maybe there are K mark states, W1, W2 up to WK. You see, nothing really changes. The calculation will become slightly more complicated, but if you understood the intuition, what was the intuition here? This was all a subspace containing all the bad states. This was my good state. Now, this will be the subspace of bad states. This will be the subspace of good states, right? So this is how it changes. Everything else remains the same. Nothing changes. So you are still doing the rotation, getting it closer to this W. Remember, now W is not a single state. It's a subspace of multiple correct answers. So when it has become very close to W, what happens if you measure? You can get W1, you can get W2, you can get WK. All of them will come in equal probability. So if you have, if you say have two mark states, yeah, sure. I'm almost done. So I'll just stop for 5 minutes before going to the codes. So if you have say two mark states, then the probability that you get say W1 is roughly 50%, probability you get W2 is roughly 50%. And you can take it to K mark states also. Okay, so I guess we can actually stop here for say 5 minutes, and we'll come back with again a short session, a shorter session than this maybe, for the seeing a code and just a few more comments on that. Okay, so we'll see you in say 5 minutes or something.